Thanks everybody for joining. I know it's been a long day for many who have actually stayed with us from the beginning, but a lot of the work that the students have been working on and developing and researching and speculating and problematizing very much obviously has a lineage and a history. And I think a big part of the way that we see research within the DRL is a kind of evolving practice, particularly very design-oriented and very much trying to explore systems, computation, the problems of materiality, trying to think through time. There are a lot of conditions and constraints in terms of working with things, and at the same time, we have a very proactive attitude towards looking at new tools, ideas of information and space that are very much part of the everyday of today, and to use that and to speculate. Okay, there is a bit of an ice experiment here. It will fall and crash during the lecture. It is a bit of a ploy for John to see if it will distract him. I put a wager that it won't. As part of the events, as this is day one of a two-day thing, we have what we call the DRL keynote lectures. And these things are really very important for us because aside about presenting the work and discussing it in sort of conversational form, it's really to bring, I think, people that we have admiration and respect, to continue the conversation, to help shape, I think, the discourse that is happening with the work that is shared between the tutors, the students, and usually are working over 3 or 4 year speculative agendas that we sort of set up. And this is the conclusion and the beginning, I think, of the second year of what we're calling behavioral complexity. Now, John, I don't think needs much of an introduction. Within this space, John and Julia, people like Cedric Price and Gordon Pask, we're really trying to tease out certain aspects from the 60s and 70s, 80s, and into the mid-90s about the role of computation. I think a lot of those early experiments, thought experiments, discourses about cybernetics, trying to explore kind of new tools and how that would refigure and reconstitute the role of the architect has been, I think, part of our conversation and I think continues. And I'm very pleased that John is here to be part of that continuation, as well as Julia and ex-students of John's and Julia's and so forth. And with that, I think I'm not going to give any more of a kind of glorified conversation on my side, but I think it's really important that I think if research is supposed to really matter and practice and design is really a big part of the way that we sort of evolve projects, then it's important that the history of this is very much embedded as a continuation of this kind of experiment. And I think from John, I've learned personally some very particular aspects. Particularly, he made a statement once that the role of computation is basically to allow us to change how we habitually work through things. It's not necessarily about computation or the literal tools, but it's really about the intellectual discourse that is as much a part of the way that we think, problematize, and work with these things as it is in terms of how we embed and push the kind of discourse, intellectual project, and material realization. So with that, I would really like you to warmly welcome John back to the AA, though he's never really left in some capacity.
Thank you, Theo. I'll start with your remark you've just made. Yes, we used to do a thought experiment called Computing Without Computers. This was partly to do what Theo's just said, which is to try to clarify the fundamental issues underlying computation and how it would let us see the things we did maybe without computers better. It was also because we hadn't got any computers when we started. The AA didn't have a single machine. Subsequently, I slightly changed my mind. I've come to the conclusion this wasn't a question, which is computing without computers, it was a statement. It really is best to do without them. Just think what it is you could do if you had this immensely powerful machine which could and would do everything. The question is, what would it do for you? The continuing experiment, that's what the AA is about. This is James Gowan from about the 125th anniversary of the AA, 1970s. A continuing experiment. And when Theo asked me to write a little piece for his Adaptive Ecologies book, I picked on James Gowan and the idea of a continuing experiment and how all these things fitted together. And Theo's kindly just suggested that some of what's going on may owe a little bit of allegiance, and I will spend the first 15 or minutes or 20 minutes or so doing a little bit of nostalgic, self-indulgent reminiscing about what we did do, and then I'll move on to what is now going on and what happens subsequently, and try to end by putting together what the total theoretical picture looks like now as best I can explain it. But we're here today to celebrate this event, and I must say how very much I have enjoyed today and how I have indeed myself learnt things from it, and it stimulated my thinking. But going back to how this started, I had taught at the AA before in the 70s, and I'd left to go and do something in Ireland, and Alvin suddenly rang me out of the blue and said, would I come back and run a unit again? Now, he got fabulous units at that time. There was Saad, there was Ron, there was everybody you can think of, Rem. And I kind of said, well, he said, it's all great, but he said, it's kind of like all the same. And he said, can't you come and do something different? So I tried, and for 2 years I tried, and we did projects like An Exploratory of Space and Time, trying to push a new agenda with Melissa and with Cedric. And basically it failed. But let me just say a couple of things happened in that preparatory period. First of all, we set up a unit tutorial space in St. Catherine's Dock on board Watchmaker. And to do that, that's the logbook from Watchmaker. You can probably barely see the printed. But here, for example, Cedric, Paul Finch, Nick Grimshaw, Izzy Metzstein, a party with Alvin and Peter Cook and Hazel and everyone were there. And that's how the boat came to be in St. Catherine's Dock and still is. That's where Julia lives during the week while she's running the computing here. But it was a vital base. And the point was that every Friday morning, Cedric and I took it in turns to invite a guest. And every morning at 8 o'clock, this is partly in revenge at students wanting to come in at 10 or 11 or 12. And the interesting thing was that in all that time, none of our guests ever made a comment about the fact it started to date. And since we had champagne and salmon and scrambled eggs at that time, it was amazing that students turned up. So that was great. But at the end of the 2 years, the problem was, oh no, before I go on, we did a few preparatory things in that time. One of them was we went to visit Ron Holland. This is a yacht designer in Southern Ireland. And Ron works with a remarkable balance between his intuition, his skill and judgment from his experience. There you see him eyeballing the lines of a boat, the splining of the boat. But he combined that with the most advanced computer techniques then available, Intergraph systems, all tucked away in this little college in Cucurbin in Ireland. And from them, he was able to do the difficult bits, like the calculations, displacement, waterline length and everything, and produce the drawings, from which the instructions went off to cut the aluminium profiles in a German shipyard and then construct the boat. So in effect, Ron had become a kind of digital craftsman. He'd regained that control of the manufacturing process that we lost when we took to doing drawings. Architects lost it when it did drawings. One of the nice things about today is these robots, for example, have got back that control of the total construction process. And I think that's very important. So lessons from people like Ron Holland, we were interested in everything from a computer-aided design program right through to the CNC and manufacturing, and that was ab initio. But anyway, I felt that we weren't changing anything, and I went to Alvin and I resigned and said, well, the problem was that I thought I was running interesting projects, but if you look at the end of year exhibitions, they're exactly like everybody else's work because the students go around copying each other. And whatever's fashionable gets replicated right the way through the exhibition spaces. And Alvin didn't like that remark, of course, but he did have to concede it was true. He said, well, what would I do to change it? So I explained how I would run a radically different kind of unit, where we didn't do any drawings, we didn't do any kind of buildings, we did basically research. And Alvin said, well, why did you do it? And I said, well, we wouldn't get any students, we wouldn't get the numbers, we would never get it past the external examiners. Anyway, the AA hasn't got any computers. So Alvin said, well, okay, we'll run the unit under numbers, I'll subsidize it, and I'll give you 5 years, because it'll take you that long to get this going. I'll give you 5 years to try to show that you can do an experiment. And I'll give you the most difficult examiners we got, who in the first year was Peter Carl and Leon van Skyke, and you will be able to persuade them. And that left the problem with the computers. So Julia and I had a software company at the time, so we simply gave the AA a lot of computers and plotters. So then we started this new unit. It started as Unit 11, but it started as 14 initially. And it was to do with morphogenesis, basically. And we still had Cedric as an advisor and Gordon Pask. And we got Pete Silver, who was at the time one of the students, and Guy, who'd also been one of the students, in as technical tutors, and we started this experiment. So year one, each year had a different title. Year one was to do with rule-based generative systems, and we built a universal constructor, which is this machine. It's a reconfigurable three-dimensional array processor consisting of a 12 by 12 by 12 matrix of cubes, each one of which contains a microprocessor chip, 8 LEDs showing the state of this space. It's a 3D cellular automata, except it's reconfigurable. It's an input and an output device. It's input because you can rearrange the cubes to set the computer a problem, and it's an output device because it had little LED lights it flashed at you if it wanted you to interact. We didn't have any robots, but anyway, I quite liked the idea that it would solicit human interaction. So that's what it did. That was the output side. And the unit designed and built all the cubes. The cubes are Ulster money boxes for children. You can see the little cheap valve. We had no money, is the problem, but we managed to build it, and it worked. And it, as Alvin famously said when he saw this running, he said, well, he says, I suppose the first 200 million years of evolution were pretty slow. He said, but it would have been quite an exciting time to be arranged. Actually, I think he said it was boring, but... And then we also, right from the start, had intended to automate this. And there was a provision for putting motors throughout that whole system. In the event, only a small bit of this got built, but these are little stepper motors driving an automatic splining machine. That year got its first honours from Matt Waltman, and we got a succession of honours from then on, I'm pleased to say, which helped to recruit students. So that was our end of first year exhibition with this object in drawing. So there were no drawings, there were no buildings. So for the first time, the AA had finally got rid of all. Now, to everyone in this room now, it seems so normal. You look at all this work we've been seeing from DRL. Don't question this for a minute, that the fact that, we see the plans of a house where there's no sign of the loos or the bathroom, which anyway you discover is tipping, and anything else. And this seems perfectly reasonable and plausible now, but it then wasn't. It was outrageous. So indeed, we did have some difficulty with the external examiners, but they were both very clever, intelligent, interesting people, and they just argued and argued and argued with us, and said yes. So the next year, we went on to explore responsive systems, in particular neural networks, feedback, trying to get beyond the algorithmic approach. We built, one of the students, Miles, built a neural network that year, and an attempt to get beyond serial computing. Also, some of the students, like Stefan, were still working on last year's project. He'd gone off to Columbia, and he had this sequence evolved just from a particular configuration of those cubes. It's a 3D cellular automata, but instead of having just alive or dead, like the life game, each cell in those days, because there was 8 LEDs, had 256 states. So those states map to things like map to things like geometrical transformations. So it starts off by deforming, stretching, rotating in response to the digital number of that space. redefine architecture as simply being logic in space at this point. Third year, we went to antennae. Every student built an input antennae and an output antennae, and they all interacted. So we had bodysuits and piezoelectric grass and interactive jewelry. We also built, we always had a hands-on thing. So we built, for example, the solar protractor. Ken Yang commissioned a unit to do some work with him in Kuala Lumpur on solar angles, and this was just a way of understanding for any point in anywhere in the planet, any particular latitude, any day of the year, any time of the day, exactly where the sun would be. And that, of course, linked through to computer programs, because we always felt that there's no point having a computer program until you could properly understand the sun's path from your own experience. Also that year, Ichiro managed to combine for the first time a cellular automata and a genetic algorithm. You'll find by the time I get to the end of this talk that I actually am very uncomfortable with any of these techniques used in isolation. I don't think you start to get the real power of any of these systems until you start to have something like a learning program, like a genetic algorithm, running with a generative system like a cellular automata. And I'll return to that point. But Ichiro simulated the response of a structure to various environmental factors, because always we had to put the project in an environmental and social context. This was very important for the unit. It wasn't just research in abstract, it was research in response to real environmental and social problems. And so these were envelopes of possible structural opportunities within that environment. At the end of that year, we built the Universal Interactor, which was all the different students' input and output devices all interacting in one space, in the North Jury Room. And again, of course, no drawings. This is the first time he had an exhibition where absolutely everything worked and communicated and interacted. Is this about to collapse? I'm watching with some interest here. Not because it would distract me, because I'm just as fascinated to everybody else to know when it's going to fail. So there were sound systems. This is Will McLean, How and Will with interactive sound systems. Body suits. This suit gives you a massage. Nicola's in the audience somewhere. Nicola and Sweeting. There's an input device. You touch this, and it senses you. And there's another one which you wear, which provides somewhere else, somewhere remotely. It can be, of course, with the stimulation that you're providing. That idea, amongst many others, has been copied all over the planet. There was Sweeting with piezoelectric grass, which responds to air movement, wind movement over little piezo grass structures. And all these systems are interconnected, so you could plug that into the massage suit, for example, and be massaged by the wind. There was an antennae, ADI, this is a Fry Otto structure basically, but round the base here were 12 extremely powerful electromagnets. So this thing thrashed about in this cage, and it really was dangerous. And it used to go into different moods. Since the exhibition knew if there was anyone in it and where they were, if it came close, if you went close to the cage, it started to rattle about to attract your attention and show off. If you're in the distance, it might just tap the cage. If you walked out of the exhibition without looking at it, it thrashed around or went into a sulk. It eventually thrashed itself to pieces 2 weeks into the exhibition. So we assumed it was getting pretty frustrated with the audience reaction. But because everything was interconnected, people, as they went in and started playing with one thing, were very surprised, to discover that it was then causing something else to interact. This is Nicola again with jewelry. The question is how you're going to control. This is basically a 3D cursor controller built into jewelry. And that was controlling this thing, which we call, or Nicola called, bendy balls. I don't have a decent photograph of here, but you can see it here twisting itself into different shapes, like an elephant's trunk, really. But it was all being controlled with these variable resistors in the jewelry. But the most extraordinary thing that year was this discovery, which is to do with fault replication. We were using close packing, the geometries of close packing systems, as our fundamental database. as a way of structuring the data. But Nicola noticed something quite extraordinary. There are two ways of packing. I'm sure most people in the room know this. You can pack alternate layers A, B, A, B, A, B, or you can pack A, B, C, A, B, C, A, B, C. But you can combine them both. So there's normal close packing, in this case some ball bearings. Here is a fault line. Now that fault line has been induced by displacing some of those. So some are packing A, B, A, B, A, B, and some are packing A, B, C, A, B, C, A, B, C. This is the notion that information is dislocations in the system. Otherwise you have white noise. There is no information until there's a disturbance to it. This is getting good. There you go. On time. The third layer, though, here we go, is it repairs, there's the fault line. The next layer, packed in, repairs the fault line, which is the most extraordinary discovery. And we wrote to all the crystallographers that we could find who are interested and knew anything about this. They all said they had no idea or never seen this before and fascinated. But this was the real shock. If you build a fourth layer, the fault reappears. So what, in fact, we've got here is a physical idea, a physical manifestation of a self-replicating fault system, a self-replicating system. And the question always arose, okay, we understand about evolution, but where did DNA evolve from? What was there before DNA? And Richard Dawkins posed this question in The Blind Watchmaker. What was the precedent for the selfish gene? What was it that was driving to replicate? And he suggested perhaps it was in clay, and suggested this person called Cairn Smith who had said this, Professor Cairn Smith. And Cairn Smith, when he saw this, was absolutely over the moon, because he said, here I've got a real demonstration of a self-replicating system in a mineral prior to the chemistry of DNA. And of course, DNA is a crystal structure. So this is not at all surprising. Nicola cast that in rubber. That's the fault line there. And there's the fault picked out. So you may be looking there at a very early ancestor, some 500 million years ago, probably. In the fourth year, oh, Nicola got honours for that, by the way. On the fourth year, we got to form generation, solar geometry. Oh, we'd already had that, never mind. And other folding was very fashionable at the time. And I was greatly amused to watch all these units struggling to put folded structures into the computers with the dreadful interfaces which were available in 1992. So Tim, as a bit of a piss take basically, built this blanket with cells in it, light-sensitive cells. So simply all you had to do was fold and manipulate your blanket. It manipulated these folding structures. This was done purely as a wind-up to the units who were into this kind of thing. But it did make quite a serious point about tangible interfaces and about interfaces that went beyond scripting and things. I mean, I said before, if all we've done is replace drawing by scripting with a typewriter, what have we achieved? I mean, nothing. It's ridiculous. It's not the way to do it. And that year we built an interactive structure with light-sensitive sensors on it. It's a little tensegrity structure here. And as the light from in the exhibition space, there was a powerful light swinging backwards and forwards on a motor. And as that light impinged on the structure deformed, and then that was projected onto a screen that hung across the entrance to North Jury Room. So as you passed this, you saw this structure moving and changing and responding, and of course drew people in to find out why this was happening, and it was just simply this structure here responding to the light changing. By year 5, we got to the notion of a genetic language of architecture. If we're talking about genetics, how did we describe them? We needed a language. We also demonstrated hierarchical cellular automata, and multi-state 3D automata started to go into the scientific literature. I'm going to keep referring back to this point because one of the things I played, there's a recording in the library here of the lecture I gave 20 years ago to the day, more or less, and I said that there was a secret agenda, which was we were borrowing all these ideas from science. I wanted to pay something back to science. And so I got very excited when I started to discover that scientific journals were starting to publish serious reviews and discussions of what we were doing. And this is the first of several examples. There are now something like 20,000 scientific publications that refer to the work of the unit during that time. This was quite fun, just a sort of diversion, and she had a 2D cellular automata running on a torus instead of in a flat plane. You know, obviously, if you're 2D cellular automata, you can pretend you can join the two sides of the screen, or the top and the bottom. In this case, he just made it into a torus. And the nice thing was that it had a kind of beginning, and this thing would kind of eat itself up. So the music kind of formed a natural climax. I'm sorry I don't have a tape, because it's actually quite nice. And this 3D demonstration by Manet Rastogi was one of the first to fully show something moving from a single cell, in this case a cube, to various structures. I'll just run a little bit of this clip while I catch my breath and have it right. Just like the life game, this 3D cell is looking at the cells around it for its neighbors. Only instead of having just alive or dead or being about to be born, there were some, I think we had 16 million states by this point. It's looking at these states, including invisible environment states here, and they're discussing on the basis of that how to construct the next part. We're all born as single cells, and those single cells start to split and split and split, and after only about 50 splittings, it turns into you and me and the rest of it in the room, or the trees out in Bedford Square. It always amuses me that, that about a third of our DNA string is identical to the trees out there. So we're all the cells are initially identical, but as we develop, we start to get more specialist cells at a certain point. The cells in our eyes, for example, are different. And the same happens here. After a particular point, this thing reaches a sort of stasis and then starts to generate differentiated cells. Hurry up. What time's dinner, Theo? Anyway, it's starting now. It's starting to change its geometries, change its color, and turn itself into something where the cells are more specialist. We can go on now. But it also had a genetic algorithm. So not only was that the output of that particular run, but these are outputs from other runs. So in other words, we got past the idea that we're likely to have some kind of merely permutations on a fixed outcome. By this point, we got to the stage where things really could evolve into some radically different kinds of structure. By year 6, we built the interactivator and the exhibition, which is what I'm personally celebrating with a few of my unit colleagues tonight. 20 years ago, we built an exhibition in the exhibition space there, and it had the first exhibition where something evolved in it, and it also was on the internet. It was the first exhibition you could virtually visit on the January 1995. Just think, I bet very few people in this room ever got on the internet before 1994, middle of it the earliest. Any hands up for before that? Very few. And some of you are obviously far too young to possibly. So we had a little book, and we had a little open the exhibition, and we built the exhibition, and Julia spent most of 2 or 3 weeks on the floor wiring all this up. Now, this is an important part of the story, because we got a grant from the Arts Council to build this exhibition. And you know how you don't read the small print? Well, I read the small print and discovered to my horror that I'd signed that this exhibition would travel to 6 other venues. There wasn't a chance of moving all this masses of wiring and computers, the whole of this space under there was stuffed with them. And so in a bit of inspiration, we said to the Arts Council, well, it will travel virtually. And he said, what on earth do you mean? I said, well, we'll send the system all over the world and people can interact with it from anywhere. And up to that point, we hadn't actually thought of that. So suddenly we had to build in this idea that anyone could interact on the internet from anywhere. The Arts Council said, yes, that's all right, so long as you hang a notice next to each of the computers that does this, saying this was funded by the Arts Council. So we had to print this poster and post it to all our friends and say, please photograph this next to your computer and send it back. So we got away with that. That was the book. And that was the exhibition, and it contained all the interactive objects we've been talking about, including the Universal Constructor from 5 years earlier, which we managed to restore and got working again. But the important bit is right in the middle. Oh, sorry, I must mention this in passing. This, another model by Nicola, is of one of these data structures based on close packing spheres, but in this case, instead of having to close pack the spheres, there are nests of LEDs which change colour and can be reconfigured to show that all possible crystal structures, for example, can be fitted into this database. That's another thing that science didn't know. Even Fuller, who was the first to propose the idea that nature had a geometry which was isospatial, didn't realise that you could fit all the crystal lattices in. It took Nicola to realise that by doing a phase change. And I don't have time to explain this, but this is just pure genius. But right in the middle of the exhibition was this. There were 3 computers, one evolving a space, one taking information from the internet, and the other examining the situation in the exhibition space. And just here on the edge of the photograph, are a whole lot of switches, which were genetic switches. So visitors to the exhibition, literal visitors, could go and switch the genes on and off and see how that affected the way the structure was changing. And in the meantime, the environment, which was always important to us, was also being sensed for noise and humidity. So the exhibition space was very noisy or smoky, as it could be in those days. It tells you how long ago this was. You could still smoke in the exhibition space 20 years ago. It would stunt the growth of the system. And the way it ran is up here are coming in messages, switches in the exhibition space, messages off the internet, because that was the point that people could make these switches virtually onto the internet. Here we got the close fitting. Instead of spheres, I'm trying to say instead of cubes, it's now spheres. And up here is the evolving form. The complexity of this software was considerable. It relied on a whole series of cycles of evolution, and it was the most complex thing by a long way that we'd achieved by that point. This was done by a group of students which contained Manet Stogie, Cristiano Ciccato, Patrick Jensen, and one of my PhD students from Ulster, who was doing genetic algorithms with me at the time. So we needed his expertise in there too. And this is the output stage. It is not an architectural proposition. I have to explain this because Peter Eisenman was our examiner this year, and he said, well, why don't you make a buildable proposition out of this? And I had a bit of a problem over that, because Eisenman got very excited about the fact you could actually section this, because I don't know what kind of dumb software he had, but he couldn't section it. But this was a real 3D model. And this is a canned animation of what happened over the 3 weeks of the exhibition, and all the interactions from literal visitors to the exhibition space and virtual visitors online managed to evolve this kind of mess. And I'm looking at this piece of ice and thinking, yes, well, in the early days, there is a certain primitiveness which you have to embrace in order to make your point. So that was what was, and it was evolving for increasing complexity. That was all. And Manet went on to do a network of computers evolving. This is collaborative communication between networks. We had a great difficulty stopping Manet networking every computer on the planet. He wanted to basically hack into. And we said, look, this is all very well, but this is the AA's name, and if the AA is known for hacking into... But he thought it'd be amazing to see what several million computers could do overnight, and we never knew. Although that came up today, towards the end of the questions, there came the notion of what would happen, there was a project just before the ice, about what would happen when you've got all these hyper-intelligent cells, and one of the critics asked the question, well, Well, we haven't got a model. It's no good looking at nature because nature doesn't have that level of intelligence in multi-cell systems. A good question. We got a series of lectures following from that, which really spelt out the range of interests at the time. Those the evolution of form, evolution of chaos and causality, generation of ideas, consciousness, artificial life, plant architecture, subconscious. That's all about plant architecture, plant geometry. I'll come to that in a minute. And in year 7, I got to the end of this, year 7, we went to Groningen and built an interactive model with the citizens there that allowed them to interact with the development of Groningen. A little in the middle of the 16th century, it's a little isolated town in the far northwest of Holland. By 1600, it had become severely fortified. We never did discover what it was that they were defending against whom, but it was a classic sort of village with a Catholic church and a Protestant church and a marketplace in the middle, and we built this interactive model which allowed the citizens there to go through it. And this is Cristiano Ciccaro's version of this, a top-down economic model and a bottom-up economic decentralized interaction. And over here on the wall, I'm looking at the same kind of thing that's still going with top-down and bottom-up. It's a fundamental principle that has to be explored with all these systems. And this is another level of complexity in this, though, because it was recursively self-similar at different levels, from the individual level through the urban to the global. I would be very interested to know what would happen if you took that diagram on the wall of the ice and did the similar thing with it and looked at it recursively at different scales. Oric Kaufmann rebuilt a chemical computer based on Gordon Pask's work. Oric was the last student to have a tutorial with Gordon before he sadly died. But this chemical computer learns on the basis of feedback, and she used that to build a simple cellular automata, which built one. This is the Siboga site we were using as a demonstration, which led to propositions about how the city might evolve. This is Cristiano's model of the whole system. There is the evolving city model. Out here is the crucial thing of the user interacting both bottom-up and top-down. Over this side is a gene pool of genetic descriptions of this city. Up here is a neural network, which is looking for identifying successful behaviors. And down here, genetic algorithms, which are rewarding successful outcomes of the bottom-up. This model actually has all the critical elements in it. And then Chris linked them all up, and here he has, this is actually his final presentation for his diploma, and there are the computers of different cities around the world all communicating with each other to share information to define evolving models of a form for a particular city. 4th of July 1996. That same year, Gianni Borsford, his project was, the way we worked, as it probably gathered, was the way we had each of the unit had one shared project, like a model of Groningen, or the Universal Constructor, or whatever it was, each year. But then each student also did an individual project with it. So in this case, they're all collaborating to build the model of Groningen, but Gianni's role was to look at solar logic in this. And it's again another interesting example of top-down and bottom-up, but in this case I'm showing it as an idea of an active tool. Let me just define that. A passive tool is one which is post hoc. Say you design a building and then you analyze its thermal performance. That's post hoc analysis after you've done it. Very useful, but you've got then to go right back and change the model. Active tools are there right at the time when you're at the tip of the creative diamond, you're having the first ideas, the first sketches, the first propositions are being put down. Those are active tools which tell you right there and then. So in this case, these are points in space, these little balls represent, about which analysis has been done on each one before any design's taken place, so that the designer knows the characteristics of all these points in space. From that, they can generate envelopes of possible solutions And from that, you can generate an actual solution. And I'm going to show Gianni applying, because all students I've been talking about went on to apply the thinking they've been doing to real projects. And I'll just touch on that in a minute, because I'm now moving on to the developments post-1996. Of course, there was continuing work at the AA. Of course, there was the establishment of all the groups like DRL and MTO, which we've been enjoying today. There was take-up at other schools of architecture, which I'll touch on, and there was further work by the other members of the unit, either in PhDs or theory or practice, and I'll touch on each of these. This is Gianni in practice. The site was this old factory, completely surrounded by houses in Notting Hill Gate. Got planning permission on the condition that there were no external windows. So there you can see under construction, there are no windows because it's being overlooked by all these adjacent houses. The problem was, because of the low sun angles in London and because the higher buildings all round it, the question was how ever to get sunlight and daylight in. So, of course, Gianni built an active tool. With the help of Arup's engineers, these spheres in space are the points which get particular levels of solar penetration all year. Do you see they don't come down all that far? Further down, you've got another cluster which are at particular times, and you go right the way down to places where you can only get daylight in, to corners where you can't even get much light in at all. So from that, Gianni then mapped different times of the year, the possible distribution of sunlight, both sunlight penetration direct and general daylight, different parts of the building. And from that, he generated quite straightforward orthogonal plans and sections. There's 3 stories, and it goes down to 3.5 there. So it's all top lit, and through these slots, diagonally, direct solar penetration occurs. I took this photograph just before it was handed over to the client, just finishing, I think it was the 26th of November, and even with the very shallow sun angles in London there, you can see as you come in at the front, you can still see direct solar projection onto the walls, so you don't feel as though you're coming into this dungeon. The lap pool in the basement, you can see brilliantly lit with reflected solar light. And of course, you chose surfaces to exploit this to the extreme. And later on, you can see it when it was taken over by the clients. There's always these shafts of sunlight coming into any of the spaces. This is right down on the lowest level, and that's a shaft of sunlight. Not all the day, of course, but at particular times, so that every space was enlivened. And that's an example of an active tool which he took over from his student project. I went to Ulster, Hong Kong in this case. I went to Hong Kong, and some of the students came with me. Guy came with me, Chris Chicano came with me, Lawrence Lau came with me, Tim Jackner later came with me. He's on with the Mats. And we had this vast horizontal space. This is worth mentioning because now Zaha Hadid has made it vertical. So at the far end of the campus, there's now a vertical building which links all these spaces vertically, whereas before we'd link. So this is the end of year exhibition, where every single student project was expected to work, to move, so you see, crawling little kiosk. But when I arrived, you see, they all made these polystyrene models. And I said, no more polystyrene models. Next end of your exhibition, the second year, and I see a button on this. I don't want a piece of paper to press. I expect to press a button and I expect it to work. And I had to say, although I really enjoyed today, the big disappointment was didn't see anything running. So we built a global virtual design studio, which allowed us to do this, which is equipped with the AAs. This is how these links kept on going. There's Moisen. This project here is from the AA and is being projected from this lecture room. You'll see there in a minute some students. These students here, the shadows, are in Hong Kong. That's Moisen and myself here at the front talking about these projects. And this is very weird because we had massive computer power there. And the AA students had never seen these flights. That see, is a AA student standing in the air, explaining his project to the students in Hong Kong. And there's his fly-through, which he's never seen because they didn't have the processing power at the AA to do that kind of thing. So this is the most extraordinary kind of event using the technology at both ends of the planet. And also there we rebuilt the Universal Constructor. Smaller, better made, but it was used for different purposes. In this case, it was being used to teach programming. And again, Cristiano is using it to teach the students how to program. What he's teaching them to program is how to drive little robots. And it's being done by each of the chunks of instruction code being represented by one of these cubes. So all they have to do is stack them up. That's Tom Fisher, and that's going to be Cristiano, no doubt. Yes, trying to talk Cantonese. I turned the sound off. And what they're doing, they programmed a robot to pick up golf balls. Here, they'd find the golf ball, pick it up and put it in a box. But it's a simple programming task, but we were using the universal mapping capability of the Universal Constructor. That was an educational thing. So this is really just to emphasize how these tools and techniques spread all over the place and being taken up in different ways. And Yasu was all being the intention that the Universal Constructor would move. And I just showed that little clip of Pete Silver with the splining. Yasu finally built the motorized version of this, and this is how the Universal Constructor should have looked in 1996. It took us a while to get to the technology where we could do this, but it's obvious how it's operating. It's responsive to gesture and movement and hand proximity and so on. And because this is Hong Kong, a piece of advice, if ever you take a really dull job, like being head of School of Design or Architecture or something, or dean, make sure you demand a vast dowry, because you only get one go at this. So I had some 14 million to play with, so we bought every piece of rapid prototyping you could get in 1996. So we had printers, we had laser cutters. Oh, the laser cutters. I had fashion, not just architecture students, I had industrial design students, and I had graphic students, and I had fashion students. They were wonderful. This laser cutter, the first people to get to it, fashion students. What did they do? They cut. That is leather cut with holes made by the laser cutter. The health and safety people who'd installed the air conditioning hadn't imagined the smell of burning laser cut leather. It was worth the embarrassing discussion with the president of the university. And the fashion students are great. So this is a printer, but it prints onto fabric, so you can make the clothes with the fabric. And this is a knitting machine that makes clothes knitting, and you can make a complete bodysuit. You can have gloves, hands, toes, the lot. So long as there's one hold left, and it's not made in bits that you stitch together, it's woven, knitted as one piece. So having to control and understand the software for all these different kinds of machinery was incredibly good for the effect it had on the environmental design students, the industrial design students. So having all these disciplines together was great. Now, of course, we had routers and 3D milling machines. Oh, and the fashion students got to that first too. They started machining themselves Perspex shoes. At that point, they were only used by a certain kind of girl in Hong Kong. And then we moved into industrial design and started to do things like evolve telephone handsets. And indeed, some of these pieces of software have been used in industry. You may well have a telephone in your pocket that was designed by that piece of software. Some of the students went on and did other things for other architects, like Guy. This may not show it, and sometimes it's very surprising, but actually, these towers have actually been designed using active tools to do with the lighting, sunlight, and so on. This is Morphogenesis. Manet very cleverly named his practice after the unit, which I thought was brilliant. And so he's now got projects all over the world, as you can see, and awards all over the world. And he's still using basic unit ideas to generate form. This is to do with solar angles. He's got his solar geometry wrong, by the way, which rather amused me. I hope he's listening to the tape. Manet, he's coming on Monday to the party, so he'll hear about this. But all these things, zero energy, zero water balance, zero waste discharge, all these things are the kind of preoccupations of the unit, and he's using those unit tools to develop these ideas. And sometimes in rather surprising materials. And this is Cristiano working for Zaha, Soho Galaxy. The whole of these exercises that we've been concerned with. This I have to say, Chris missed the presentation, but this is it, Chris. They have a, right at the back, they have a quadcopter which flies around depositing ice to make these shape, and exactly like this. It's perfect. You could have saved a lot of work. But Chris, not being able to do that, had to look at the complexity of shape, how to minimize the number of particularly complex, difficult geometrical forms which were going to be very expensive to develop in order to maximize the simple plane curvature areas in order to make the overall project fit within budget and so on. So it's still applying these kind of fairly sophisticated computer analysis techniques and generative techniques, but for a real project. Variable geometry presses, obviously all computer control, producing the panels, double curved panels, to construct the complexity of the curves of the architecture. And some of the students went back to doing theoretical work. There's Nicola, whose fault replication I showed earlier. She went back and did a PhD with me, and one of the things which she developed, amongst others, was a proper theoretical analysis of this fault replication. And again, that's another idea which has passed very firmly into the scientific domain. This is Patrick Janssen. He went on, I'll just show a little clip of his in a moment. McLean, Will, went more into publishing, amongst other things, and teaching, and same with Sam, who is about to publish the collected works of Cedric Price, having previously produced 3 other volumes about Cedric. Of course, that makes another connection back to the interest with Cedric and his role in the unit. And then, of course, that brings us to today and the exciting projects we've seen around this room. Now, I just want to say a little bit about the theory. Out of this, there are many parts of theory out of this, and I'm just going to be able to deal with one, which is the evolutionary digital design process. Now, I'll skip through this quite quickly. It runs like this. Like every architectural project, it has to have a generating concept. This is not bottom-up at this point. This is top-down at the start. It goes top-down into a seed, and I'll explain a seed in a second. The seed then goes into a gene pool, and at that point, this becomes a more bottom-up process as it goes through reproduction, development, prototyping, analysis, selection, and eventually materializing or being recycled. And I'll skip through this quickly. My analogy has also always been the idea that the acorn always makes an oak tree. They're always recognizably oak leaves and oak trees, but every leaf is different, every tree is different depending on its environment. And that analogy has just been taken up by Google with a project they're proposing where they're hoping to make 200 billion a year or whatever out of the building industry doing this. Plant architectures and body plans we've heard about today. Fascinating. There are only 24 or 26 strategies which nature has to make all the different trees in the world. And that economy of means is something that's very powerful to us. And the notion that we need probably body plans. And every plant, every tree can be analyzed as one of those types. And that produces an incredible richness. There seems to be an obsession in architecture that if you have types or generic ideas, you'll somehow get endless repetition. Nothing could be further from the truth. And the same with body plans. This is the same body plan being applied to different forms of animal, fish, and birds. So the strategies of nature are fascinating and relevant. So then we come to seeding, and at this point I'm going to briefly go back to my own project. As a student at the AA, I was struggling with this little structural system which consists of just 2 structural units. Because in those days, you see, we thought we had to have mass production, so the dies are very expensive to make this, so you had to minimize the number of units. So there were only going to be 2, and there were going to be no cut units. You're going to make straight line edges by just by the way you turned round the different units in the system. The problem was one of drawing it, and when I was a student, I had to hire a flatbed plotter by the hour, and as I was saying to someone, there was no preview. You would just have a stack of punch cards, right? So you had no idea how big this drawing was going to be. So you'd fork out all your dinner money for a month to go and get this drawing done in the lab, and you'd turn up, because the AA didn't have a plot, it didn't have a computer, it had one teletype terminal to remote time sharing. That's all the AA had then. And when you got there, you found that either it had plotted the whole thing off the piece of paper completely, and it's just a puddle of ink at the side, or it had dug a hole in the middle of the paper, or it had whipped backwards and forwards across it, slashing it to pieces. And there was your precious time and your precious piece of Whatman paper gone. And so finally, the triumph of managing to get a drawing onto the piece of paper. And I was touched to the core today when someone was talking about the robot that kept on trying to put the pin back in the cup missing. And I thought, yes, I know all about that. The triumph when it actually goes into the paper cup. The triumph when the drawing's actually on the piece of paper. So I had enough of that. So when I got to Cambridge, I started, instead of putting all the individual code, because there was no AutoCAD. You had to write every piece of software from scratch. You had to write everything. To put in every vector, every perspective program, you had to write yourself in Fortran. It was agony. Got to Cambridge, and I thought, bugger all that. I'm gonna put in a minimal configuration of these things and use the power of the computer to do a bit more than just draw it. And so that is the minimum possible configuration of my structural units. There's just 2 still, but they're in 32 different orientations in this closed thing. And it's closed so that it will expand and not get holes in itself. That, in 1969, was the only graphics display device in the whole of Cambridge University. I say that because if you look at a copy of AD at the time, you'd think every architect had a computer on their desk. No, none of them had, not a one. And of course, they also said there never would be. Ha! Well, both those things changed, but it's a real computer. Look, it's got flashing lights like in the movies. But the screen hadn't even got storage capacity. It draws like this by flashing the beam around, and it slowly fades. So if you try to do a drawing that's too complicated, the beginning of it's faded before you get to the end. So that keeps you to be fairly simple. That means I can show you these very simple drawings. There is the seed, just simple instruction, grow. And magic, it grew on the screen. Shear, I could cut the structure. Bend, I could bend the structure. And basically it was this. Instead of putting all the data into the data structure, you just put a seed in. And then you had a cultivation program which enabled you to build that data structure round and round and round and round and round, doing all the work for you. This is my dream of being a computer, you see. I'm fundamentally incredibly lazy. So the whole idea that this dream machine could do all my work. But in order to do that, the problems of trying to learn to do Atlas Titan machine code programming at Cambridge and various other things were problematic. And I could only then hold one tiny dot of data, and I had to do this in the middle of the night. It's the only time I was allowed to have the computer and the graphics display device. And the important part of this story is the only other person in Cambridge who was using that at the time was John Horton Conway, who invented the life game. So he and I were sharing this computer every night for years. Not 3 years, to be precise. So that's how we did it, and that finally got you various structures. But you only got high resolution, you see, when you put them on the plotter. We couldn't put this on the screen then. It went on the plotter. Okay, so that was seeding, and then you go into a gene pool, then you go to reproduction. I don't need to explain all this. There's crossover, there's mutation. Then there are various generative techniques. There are a lot of these, parametric geometry being the one which I think most people are most familiar with. But there are others, like combinatorial systems. And these 2 bottom ones, cellular automata, which we've again hit today, parallel discrete computation, polyautomata, and procedural shape languages. The one I've just showed was written in something called the procedural shape language, which is my favorite. But you can use any of these. And that's, of course, what generates a 3D cellular automata like this, is a set of rules. So that's the generative engine. Then you have the genetic algorithm, attributed to John Holland, but developed mostly for optimization in engineering. And we suggested we could use this for experiments on design problems. And everyone said, the engineer said, don't be ridiculous, that's really stupid. Everyone knows architectural problems are ill-defined and they have conflicting criteria, and obviously genetic algorithms can't do with that. I said, hang on a minute, human life, would you say that was clearly defined? Oh, no. Would you say that all the criteria aren't conflicting? I said, well, genetic algorithms seem to have managed to do quite well. They've managed to evolve you and me, so I'm going to have a go. And so we did. And now, applying genetic algorithms to design problems is common right through engineering, right through computer science. So when it was done here in the AA, no one had done it before. And in fact, they said it was impossible. And we first did it with Peter Graham on boats, optimizing boat design. And then we start to combine these techniques. You start to combine the cellular automata with the genetic algorithm, and I showed that with Ichiro earlier, where he's got both a cellular automata generating this and a genetic algorithm controlling it from one run to the next. All that has to take place in an environment. That is crucial to my way of thinking. And so this sequence, which I showed earlier, was evolved in that environment in the exhibition space there. Just show this from Patrick Jansen. Patrick, another student who was responsible for that initial thing, he'd also did his PhD with me. And here is a series of examples from his PhD where all those have been generated entirely automatically from one generative concept. And they are proper solid models, but they're able to be first of all, they're being generated totally automatically. You can see here, it's going to pop in a staircase in a second in response to some building brief. It's deforming the geometry. And each time this program runs, it does a rigorous analysis of everything it can manage to analyze. And on the basis of that, will modify the genetic algorithm so that next time it will produce a more optimal solution. You can see it's carving holes through the center of the building, and in a moment it's going to add some fenestration, so we can skip past this. Oh, sorry. There should be well, maybe there's in a moment. Virtual prototyping. I thought I'd better show one sort of real-life project. This is One Island East in Hong Kong, which is of great interest because it was the first building to be totally procured from a virtual model. Chris was working for Frank Gehry at the time before he went to Zaha, and Frank's software, Digital Project, was being used for this. And whilst Frank was not in any way involved with the design of this building, the software wing, Gehry Technologies, was helping to structure this program. And then, that's very odd, I thought I had no, never mind. And then analysis. These are the hydrostatic calculations, for example, from the auto yacht program being done to do the boats, and that's in there. You had to perform some kind of analysis at some point. And this is post hoc analysis, as opposed to the active tools I was describing earlier. So there you see a typical run. There's a genotype, there's some plans coming out, there's a building form, there's some analysis taking place of its thermal performance. From that, there's an identification of fitness. From that, an evaluation, and so it goes on. Selection, this is crucial. Natural selection, convergent evolution is what engineers were on about. They wanted to converge on an optimal solution. They wanted to use natural selection, which means calculations, to do it. We said, no, there are three other squares here which are as important, possibly more important. You can diverge. You can use these techniques to explore different ideas. Or there's artificial selection, which is you interfering as an individual. And that came from Darwin himself. In the original book, he had the problem of selling the idea of natural selection. So he said, well, you all know about variation under what he called domestication, that is how to breed racehorses or pigeons or whatever, dogs. And he then went on to say, well, we get variation under nature as well. And then he said,
And nature, given the massive time, can do natural selection. So that's how on this diagram, that is the one which nature uses. But this artificial one, the dog breeder, is also important. You have skill, intuition, judgment, which you can use too, and that goes into this box here. And after that, some are discarded, some go around the gene pool. So here you see from Patrick Jansen's program, here's a Pareto optimization curve. All those along the bottom edge are pretty good. All these ones up here are pretty hopeless. And then it will rerun and reevaluate the performance of those prototypes. So that's a description. Oh, later on, we went on, after Patrick did his PhD, Patrick and I managed to get a big research grant. And so we started to look at all the other quantitatively evaluable criteria, leaving still the idea of your skill and judgment in that artificial selection box. And finally, materialization via perhaps building information model, and that's One Island. It's not a very elegant building to have such an important role historically as the first building to be totally procured from a digital model. And finally, I come to the end. Pit stops. This notion that all these ideas have been going into computer theory, into engineering, into all over the place. It's recently come to my great delight to motor racing. They finally realized that pit stops are a design problem. And I'm pleased to tell you that they are now using genetic algorithms with both natural and artificial selection, thank you AA, to determine pit stop timing. It's a perfect design program for a genetic algorithm. Software. AutoCAD are now producing a genetic algorithm piece of software. It's useless so far, but it will be, in the end, I'm sure, a tool which everyone has access to and will want. NASA have an artificial evolution design program, again, based on work here, which is, in this case, designing rather improbable antennae. But the final point is this. There's been a spate recently of books called things like Computational Design Thinking, Digital Turn in Architecture, about the sort of teasing notion that maybe there's a theory here. Now, I'm cautious about this. There could be a theory of digital design. I think we could all agree that. That's a very specific thing. I've just outlined a very specific theory of evolutionary digital design, which would have to be a subset of that. That's just my own particular interpretation from what we've been doing. I don't think the digital in general can be a new theory of architecture in a general sense. However, it could catalyze. It's back to the point that Theo made right at the opening, which is that thinking about the computer can cause you to rethink what you do otherwise. So I think what's going on in digital design could cause us to do a rethink of what's going on as a general theory of architecture. Computer is a muse. It could inspire us to build our whole mental models differently of architecture. Never mind using the computer, that's how we conceive it. Change the way we conceptualize architectural ideas, affect our own very own internal psychology of model building in our heads. The idea of conceiving of ideas not just for development into one project, but the idea that you would conceive of architectural ideas with the idea that they might evolve. Most architects will say, I mean, there was a nice little quote the other day from Norman Foster, no less, where he says, well, every time I start a new project, I like to think I'm starting with a blank piece of paper or a blank screen. But he said, at the end, with hindsight, I can see an evolution and development between projects. What if instead of seeing that with hindsight, you started thinking of that up front and conceiving of ideas which could evolve from the very outset? And why not conceive of ideas which could be enriched by the computer process instead of diminished by it? The old joke used to be not CAD, but COD, C-O-D, computer obstructed design. Oh, I love it. The chairman of Autodesk actually went on like proudly the other day saying, you can tell which of the projects in the 90s were designed with AutoCAD because of the primitive forms. I'm thinking, and you're proud of that? You know. So I think we have a problem there. So there's the process, summarized. You conceive of an idea, you encode it, you breed it, you develop it, you generate it, you analyze it, you select it, you evolve it, you materialize it. Said in full, you could start to say, instead of that being just in, you could start to apply that to any design process. You can start just crossing out words that are to do with computing. So I think we're moving to a point where we're going to be able to change the way we accommodate new and different ways of thinking. And I think we've seen some very nice examples of that today. So congratulations to students that we saw. But right at the tip of the creative diamond, where there's a gem of a new architectural idea. And I think that will change the balance of the roles between architect, client, user, computer, and environment will all change. And I think that could lead to a new theory, a new kind of process, a new kind of creativity where we think about that creative process differently, and a radically new architecture, perhaps. Thank you. How are you doing? What time have we got dinner?
I think we got a little time.
Okay.
Yeah. John could answer a couple of questions if anybody's interested. There is a floating mic. The way it works, you raise your hand, floating mic will come to you, you ask the question, you get the answer. Is there any questions? Everything was super clear. We could go home and have dinner. Yeah. Is there any questions? Going once, twice. Sold to nobody. Okay. Thanks, everybody. Then let's thank John. If I can just make a quick announcement. Tomorrow we pick up day 2, 10 o'clock, same room, same scenario, different keynote speaker. Thank you.
Thank you, dear.
Thanks so much, John. That was great.
John, I had a question. Did you
To our dearest